Maybe we'll pretend it's almost 100.
Yeah,
How's that?
90%.
Okay, so anyway, so good morning, good evening, good afternoon, everybody, because I know that we have people from all over the globe, which is really wonderful. And it's a real great pleasure for me actually to be introducing the topic today and the speakers. Topic because AVO-A.D.A.M, I was at the inauguration when AVO-A.D.A.M was inaugurated, and it's a pity that Ugo Amaldi couldn't be here today, but I've seen what's been going on, but we will hear the current status from our three speakers. And the first person I would like to introduce Stephen Myers, who's both a colleague, collaborator, and a friend. I've known him for a long time. And his last 2 years at CERN is when we were doing medical applications and I was his deputy, so fond memories of that. But actually, he doesn't really need much of an introduction, but I will do my job with the fact that, so he was born in Northern Ireland in Belfast and joined CERN in 1972. And he was at CERN for over 40 years. And I think in field of accelerators, he's so well known that I don't think I need to tell you anything more. The only thing perhaps is worth remembering is he was involved, of course, in the LHC, the Large Hadron Collider, but more importantly, when we had this big repair job, it was up to Steve to get everything working again so that we could celebrate the discovery of Higgs on the 4th of July. So that was really one of the landmarks, and he's won lots of honors and honorary doctorates, the International Particle Accelerator Lifetime Achievement, the European Physical Society Edison Volta Prize. But as a Brit, of course, in 2013, he was awarded the OBE from UK for services to science, and jointly awarded the Prince of Asturias. So he's not, it can be Irish, English, and Spanish in the end, but many countries. So it's a great pleasure to have you here, Steve. And for today's topic, though, he's currently the executive chair of the Geneva-based company AVO-A.D.A.M, and that's what we will hear a lot about. Because what I gave the task to Steve was, we would really like to hear about when you start with a research idea, how does that get translated into a device? And then the final step of how do you actually make it into a medical device? So our three speakers today, so Steve will discuss the beginnings of the story. Alberto Degiovanni will really tell us how do you go transition from research device into medical device. And Anna will, as a medical physicist, will actually tell us some of the clinical applications, the challenges that are facing from actually having a device and how do you make it clinically viable. I'm not going to say much more than that, but I'll let Steve Myers start. So thank you, Steve, for agreeing. Also, Alberto and Maria, please.
Okay, I hope everyone can hear me. Yeah.
Yes, we can hear you, yes.
Okay, good. So I will give us an introduction, and most of you will know everything I'm going to say. But the important parts will come later with Alberto and Anna. So I just wanted to say very generally, what are the requirements for particle therapy? Clearly, I mean, this is so obvious, it's hardly worth saying. You need to deposit ionizing radiation on the tumor. And to do that, you need to control in 3 dimensions the position at which you deposit the radiation. You need to also control the quantity or the dose of radiation. And if you can do it, you also want to control the area of the radiation spot. Now, we all know that the depth is controlled by the incident energy of the beam, that's because of the bright peak, and that the dose is controlled by the beam intensity or the number of ions or number of protons. And the area is controlled by the spot size, or what we call in the accelerator language, the emittance. Now, for emittance or beam size, it's easy to increase the beam size, but very difficult to decrease it. So the important parameters for particle therapy accelerators are clearly cost and treatment efficiency. And the considerations for accelerators which impact cost and treatment efficiency are You want modularity because you want to have ease of installation and also decommissioning if necessary. You'd like to have a small footprint. You want to control particle losses because of the activation due to radiation. You would like to have depth modulation by energy modulation, in other words, electronic change of energy, so as to avoid having to use these devices which you put in front of the beam to reduce the energy. We'd also like to have beam spot size control, and of course, dose control, and if possible, control of the transverse area or the beam size. And this is a sort of wish list. And when you come up with a wish list like that, the best accelerators are the ones which will tick most of the boxes. So if we want to do energy depth modulation, what you need to do is electronic energy modulation of the beam. And if you want to do that, if you can do that fast, it has an impact on the treatment efficiency. And this allows for more conformal treating of, for example, moving tumors, because if you have a very fast energy change, you can track it. It also facilitates, this is called volumetric repainting or 3D repainting. And this is a technique which has been shown to improve the conformity of the radiation dose distribution in the tumor. So that's very important for electronic. Now, the other, probably one of the most important points is that fast depth modulation with high intensity spots allows you to do hypofractionation. And this substantially reduces the patient throughput time and therefore increases the number of patients that you can do. It also allows you to do flash. So considering cost, particle losses, we all know that radiation activation has three costly consequences. The first one is you have to contain the radiation by very expensive radiation shielding, which increases the cost quite substantially of the installations. Some of the radiation shielding is extremely thick, and you see this in some of the installations which have been going on recently in London. Components can also have induced radiation with long half-lives, and these activated components have to be treated or destroyed, and this, as we know with CERN, is a very expensive procedure. The other thing which is important for a medical facility is that for scheduled maintenance and technical faults, it may be necessary to keep the facility closed for several days until the induced radiation has reached a safe level for an intervention. And we're very used to this at CERN. We have quite long times before we're allowed to go to certain areas to repair certain things. And we also have to follow very strict radiation procedures. AVO-A.D.A.M is one of them which we use extensively. The relatively low beam losses from a linac, and this is why we've chosen a linac, combined with the absence or combined with the non-need of mechanically moving energy degraders, significantly reduces the radiation shielding and the construction cost. That's a very important point. I lost my, there we are. So modularity and dose control. Modularity clearly comes into cost. If you can make an accelerator which is small modules like we have for this light machine, each module is a maximum of about 1.80 meters and can be shipped via standard service lifts rather than heavy cranes and so on and so forth. For example, in London, they had to block the traffic and so on during the construction of the UCLA. Small modules reduce the installation cost. You don't need expensive cranes or load handling devices. It also allows installations in what we call difficult locations. And for example, here we have Harley Street, which is a grade 2 listed building in central London. And we have where we will install, we have the plans for installation in Harley Street. To change the subject, we would like to be able to change the spot dose rapidly. If we can do this quickly, then we can have a more precise distribution of the dose and a better treatment, and that will be covered to a certain extent by Anna. Capital cost, clearly the footprint area impacts the cost of land acquisition and the construction cost. So you want to have as small a footprint as you can, and there's been a lot of progress made in all types of accelerators in the last few years.
Steve, sorry to interrupt, but we keep this, your voice keeps going up and down. Is there?
I'll try to go closer.
Okay, thank you. Thank you.
Working. I'll try to go closer to my computer. Is that any better?
Thank you. That's good.
Okay, thanks for telling me that. I had my headphones, but they ran out of battery just before the meeting. So the four components, operational costs are extremely important for these devices, and the components we all know are the consumables, and this becomes a problem due to the radiation. Maintenance costs, electrical power consumption, and also you want to try to reduce the salaries needed for these highly trained personnel, and that's one of the big difficulties because these accelerators are technically complicated devices and need highly trained personnel. Okay, for treatment efficiency and cost, for treatment efficiency, we would like to have a small spot size for pencil beam scanning. That's the more modern way of doing it. It's useful also to be able to control the spot size and keep it constant, or be able to control it over an energy range, because this can impact clinical efficiency, which you'll see later. For example, small spot sizes close to the penumbra are desirable, whereas large spot sizes in the center of the tumor are desirable. Now, the small beam cross section, this is something which we didn't realize when we started working with linacs for the first time. Let me stop my phone. Oh, should have turned it off before I started. Okay, that's my phone. Sorry about that. So if you have a small beam cross section, then you need a small good field region or small aperture in the transfer line magnets or the gantry magnets. This means you can have, with a small beam, you can have cheaper and lighter magnets. This is a fairly big impact on the design and cost of the HEVT, the high energy beam transfer, and the gantry. Insisting. So this is my summary. Sorry about the telephone. The advantages of the light linac. This is summarizing what I've just said. Electronic control of output energy allows you to have a constant high intensity at all output energies. And you'll see a plot of this from Anna. You don't need these energy degraders, which means you have low proton losses. Because of the low proton losses, you've got reduced radiation shielding. And this, because of the high intensities throughout the range, you can do high fractionation and flash. If you can make these energy changes fast, then there's some additional advantages. Facilitates improved treatment for moving organs. You've got a 3D repainting for more conformity possibility, because you need to be able to change the energy quickly. And you also can have conformal flash, because you can actually, you'll see this later with Anna. Small linacs have very small transverse beam emittances, and this allows you a small beam size, and you can defocus that over so as to keep the beam size constant, or you can reduce it to a minimum at higher energies, and then even collimate it to generate many beams. And I've already mentioned the smaller tubular magnets. The other thing, of course, which I've mentioned before, is the modular design, and this reduces the installation costs, and it also gives ease of dismantling or decommissioning if you want to move your accelerator to another place after installing. So now I'd like to move on to the transition from a research device to an industrial medical device with Alberto giving the talk. This is, I think, a very important part of the presentation. So I will stop sharing my screen, Alberto, and you can start sharing.
So thank you, Steve. So just a few words about Alberto Degiovanni. He's the Deputy Technical Director and Group Leader for Accelerator Physics at AVO-A.D.A.M. I've known him for a long time. This is always thanks to Ugo. So almost a lot of the accelerator people go through TERA. And I met Alberto when he was doing his PhD with EPFL Lausanne and TERA. And since then, he's had a PhD and a postdoc at CERN, and then joined AVO-A.D.A.M. And I'm sure we're going to learn a lot about what he's been working on for the last few years. So Alberto, welcome, and it's nice to see you again.
Thank you very much, Manjit, and thanks, Steve, for these initial slides. Yeah, we transition now from what Steve said to what we have done in the past, more than 7 years within ADAM. That is the transition from a research device to an industrial medical device. And just a second. Okay. What I will talk about, it's mainly two aspects. One is really about light accelerator, that eventually I will call it a product at the end. But the other aspect that I'm going to touch is not about the accelerator, but more about the industrialization process. And the focus here is not much on the technology, but more on the industrialization path. And this is the submerged part of this iceberg. So let's start from the first part, which is the light accelerator. And well, as Steve mentioned, we need to know what we want to do with such an accelerator. And in principle, we want to use it for proton therapy. And these define our clinical needs. And from the clinical needs and user requirements, we basically flow it down to beam and system requirement. What does it mean for a beam? In a very simplistic way, I would say, okay, we want an energy between 70 and 230 MeV and an average current of the order of the nanoamperes. And that's okay for the beam. And then also we want to be able to deliver it in a 3D manner. So we add also scanning magnets to achieve the active pencil beam scanning. But so this is a very simplistic view, but already tell us that we want to achieve beam spots and in principle with variable charge as well to cover uniformly in those the tumor. And here we translate then the charge into a peak current from our machine. We want to have variable energy and in order to cover tumor between 3 and 32 centimeters, so energies that can be changed between 70 and 230 MeV, and variable spots position to cover different location on the transverse field size. Okay, now that we have the system requirement, we can start actually the design. And the design will start with a high level conceptual subdivision of how we are going to build the full system. And in here, what you will see in this picture are 3 main parts. And maybe the final part can be similar to other machine where we have a high energy beam transport and then a patient positioning system. And we have also imaging system for the patient. But what is novel and what is really let's say, important here is the accelerator part, which is based on this high-frequency linac. Indeed, light stands for linac for image-guided hadron therapy. And in terms of main specification, you can see here the main parameter of this linac with a length of about 25 meters and maximum output energy of 230 MeV. The output peak current that is, as we mentioned before, variable in the range between 0.3 and up to 40 microamps, and within very short pulses of the order of the 0.5 to 2 microseconds. And the main RF frequency of this linac, it's the 3 gigahertz, the same as conventional linac used in radiotherapy, and the maximum repetition rate of 200 Hertz. This is what we call the light beam production system. And it starts from a concept that is to apply the high frequency linac for protons. And these use technology that is called the cell-coupled linac structures, and they are put together in what we call RF units. An RF unit include accelerator modules like this, where we have accelerating tanks interleaved with space for quadrupoles to focus the beam, and then the RF power source and RF power transport system here, which are based on commercially available modulator and klystron system and waveguide components network. So this is the initial concept, and as a concept, it started already more than 20 years ago, and first proposal and first proof of principle was actually the LIBO structure, the linac booster prototype that was proposed and then built and tested by TERA, CERN, and ENFN, which was really the first time high-frequency linac could be used to accelerate protons. This is just a single element of a full system, but it gives a proof of principle that is very important and on which we will build up. And already in the years 2009, 2010, a first unit made under industrial standard was actually prototyped by AVO-A.D.A.M company that was funded at the end of 2007. And this was optimized for industrial production, and there were already some small design upgrades, some design changes to improve the manufacturability and the production process. Now, from that moment on, really the challenge became at a larger scale, and it was to really bring the linac technology to the full system, and to achieve a pulse beam at 200 Hz, as we mentioned, an active energy modulation without mechanical degrader, and to be able to produce pencil beam to allow for active scanning or spot scanning, and to include in the design modularity and flexibility. And modularity is shown in this picture, where the full linac is not only composed by this active part where we perform energy modulation, which are the CCL units here on the right, but we need to include the full chain, starting from the proton source, going through the radio frequency quadrupole, which was developed by CERN and then tested together with AVO-A.D.A.M in the year 2013 to 2015. The first prototype was then installed in the LIGHT prototype system that I will mention in the next slides. We had then a section of side-coupled drift tube linac, which was originally designed by Enea, and some part of it were already tested in Frascati by Enea for the implant project, and then it was used by AVO-A.D.A.M in the full light design to allow the energy increase from 5 to 37.5 MeV. And all these, including also industrialization upgrade and for many units production. The same is true for the CCLs, where exactly developed within this TERA, CERN, ENFN collaboration. But then when AVO-A.D.A.M took them, it was really to improve the design and to allow modularity and the full-scale manufacturability. So once we have these as a specified elements of our system, we actually went to the first technical feasibility integration. And this was really the light linac prototype that was built in Geneva to test the functioning of all these subsystems all together for the first time. So we did commission a light prototype up to 52 MeV at different stages of energy, which are described in the table here below, by adding additional RF modules at each energy stage and then characterizing the beam. This is what we had as a prototype installation in Geneva, including the first built RFQ with coaxial power lines, the SCDTL modules, 4 of them were actually installed in Geneva, and first 2 CCL modules to achieve the 52 MeV of energy. What is important in this picture is also to highlight the fact that all this linac was installed in a very small area in this shielded bunker inside the building, which is less than 80 square meters, as you see in this plot. This is just a view of this full prototype installed, and as a prototype, maybe there is one aspect that one has to notice here, that of course some of the ancillary system and all the cablings was not fully considered in this first installation, and is something that really it has been an improvement then when we go from a prototype to a first product where you consider all the aspects. But here the goal was really to make it functional and test the functionality of all these 3 cavities type altogether for the first time. And as such, during the commissioning, as I mentioned, it was done in stages in the year 2018 and 2019. We did achieve at the end of 2019 for the first time a fast energy modulation, which is pictured here, where we could scan in energy on a very rapid scale. As you see here, the scale, it's at the 2nd level between this point and this point. So there are 100 spots with all of them with different energies across these 2 markers. And this was the very first time we could demonstrate in practice the fast energy modulation feature of the light machine. And at the same time, some testing were performed on the intensity modulation that is achieved at the source and the low energy beam transfer side of the machine. So now this was the technical feasibility part of the light, and now we are at a different stage where we actually made the full-scale integration, and this up to 230 MeV of the light beam production system. This is done in Daresbury, UK, at the Science and Technologies Facility Council site, where we did install the light machine. And this with the goal to have an end-to-end testing, not only of the accelerator, but including also the medical technical system and all the dose delivery system. That's exactly the complexity increase. And that's another aspect that we have to take into account. Going from a concept to a real product, we really need to go to end-to-end test and to complete what is called in the industrial setting, the verification and validation test. This will be then done in partnership with University Hospital Birmingham and NHS Foundation Trust. We aim to treat the first patients in Daresbury in the context of the certification plan. And I'm going to show you this video that will describe the full system installed in Daresbury. And I think that's going to give you an idea of the different parts.
The journey begins in the northwest of England at the Daresbury laboratory of the UK's Science and Technology Facilities Council, where we have set up our manufacturing site for the assembly and integration of our modular light system. To begin, we created an accelerator hall to house the gallery of accelerators, which form the beating heart of the light system. We formed walls and ceiling, and then an extra room added on top to house heavy driving units. The accelerator, currently under construction, is driven by 4 IoTs operating at 750 MHz, 13 klystrons operating at 3 GHz, all supplying RF power to the accelerators, and is cooled, kept under vacuum and monitored by beam diagnostics and our time-of-flight energy measurement algorithm. DC supplies in the system drive magnets which control the position of the beam, and a full control system keeps the entire system working optimally. The accelerator is driven from a control room where our specialist operators accelerate and steer the proton beam. Everything starts at an ECRIS, a robust form of proton source known for its stable operation and long lifetime, and with a supply voltage of 40,000 volts. From there, the protons start their journey along a gallery of accelerators moving as a 200 Hz pulsed beam, through the CERN-developed RFQ, through 4 SCDTLs, and finally through 15 CCLs, accelerating up to a maximum of 230 MeV. The patient treatment itself, which is the final goal, takes place in the treatment room at the end of the accelerator. This has also been built at Daresbury, where we'll undertake our clinical investigation plan and first patient treatment in conjunction with University Hospital Birmingham. We've installed a state-of-the-art robot chair with CT scanner and X-ray panels for accurate patient positioning. patient treatment workflow begins with patient scanning, controlled from an internal control room. Then a patient position cross-check with the robot chair ensures the patient is in the correct treatment position. And then treatment can begin. The light system offers the unique feature of electronic energy modulation, obviating the need for absorbers. This results in a considerable reduction in the thickness of the radiation shielding that's required. In addition, the light system has a very high proton beam transmission efficiency. Light contains over 34,000 separate components, integrates more than 300 separate devices, and accelerates protons up to 60% of the speed of light. There are over 250 front-end control software instances newly developed to accelerate, steer, and monitor the proton beam. It utilizes 20 gigabytes per day of data capture in beam optimization and control, and delivers a proton pulse at your energy of choice every 5 milliseconds. Light from advanced oncotherapy. Advanced oncotherapy now.
Okay, we have seen from the video the different parts, and indeed we did reach 230 MeV end of September last year, and this close a bit this section on the product part. But then I want to spend a few minutes also on the industrialization process that has been done, because if what you have seen is what is the technology application, and that relates also to the clients, to the users and patients, and also opens to new opportunities in terms of technology, well, it's actually need behind it a lot of activity, a lot of work that is more in the field of the production and commercialization, documentation and certification, quality process development and product development. And all these relates then to side activity that maybe are less visible or not so known maybe in the research environment, where actually we need to talk about regulation, standards, testing, V&V, intellectual properties is maybe something also to be kept in mind from an industrial perspective, and then supply chain management and funding, of course. So these are all the challenges in terms of medical industry to bring some technology to a product stage. And just took a couple of examples to show you, to give some aspect of this, in particular in terms of industry standards for medical device. We are following the ISO 13485 as a framework, and it relies on a quality management system for the different aspects of the development and of the life cycle, not only of the product, but also of the process itself. And this basically details on how to follow the design control, the product surveillance, resources, the management of responsibility. So all these need to be followed within a quality management system. And within this, the processes are defined, and the one that is very important to the transition from a research device to a product, it's really the design and development process, which basically start from, as I said in the beginning, user needs and regulatory requirements flows down in the design, and then in the design input for all the different subsystems, and more in details for each single item. And each of them should go through a first loop, which is called verification, that basically the design output, they are compatible with what was specified as a design input. And this at every, at the item level, going up to the system level, subsystem, and then system level, where finally, once the system is fully installed, can go through what is called the validation step, which basically tell us if our product is actually meeting the user needs and the regulatory requirements. If all this is completed, then we can go through the certification path and then commercialization. I think all of these steps take quite some time, in the order of years, I would say, for such a complex device. And this is where we are actually working on. And this is actually following a very long-scale timeline where we start from concept screening and evaluation of technology and develop a concept and then bring it to product development and then to the market introduction. So I think all this is very important, and we have a lot of examples of all these stages of what can be called technology readiness level, and moving from concept that typically come from labs and academia through collaboration to the industrial implementation. And this, I think, is also true for the case of light. With this, I just wanted to add one final slide, since we are on the HITRIplus seminar, which also deals with light ions, and up to now it was mainly about protons, but also the same technology in principle could be easily transferred to light ions, and there was already design in the past for carbon ions. There are studies ongoing as well within the NIMS study for other ions. I think when we look at helium as well, the same technology could be applied, of course, with a linac that is from this design, we could say much less than a carbon ion linac design to reach 230 MeV per nucleon. So I think that's also important to keep in mind. This technology can be extended also to light ions. And with this, I finished my presentation. Thank you.
Thank you, Alberto. So for our third speaker, we have Maria Kolano. And she's a medical physicist who's been working at AVO-A.D.A.M for 5 years. But prior to joining that, she finished her undergraduate degree in medical physics and particle physics at Manchester, her PhD at PSI, and also as a Marie-Curie CERN fellow. And she has a large range of experience in medical application of accelerators, but at AVO-A.D.A.M, AVO, she's really looking at treatment planning, dosimetry, and also investigating the feasibility of the light linac treatment for flash. So Anna, please.
Good afternoon, everyone. So just as a recap, in this part of the talk, I will try to show you how these light features translate to clinical applications with some patient examples. So just to quickly recap, yes, active energy modulation, we don't need the absorber. We can have conformal planning also for shallow targets like brain tumors, for instance. And also this would allow flash at all depths. Fast scanning, again here, very important for achieving flash dose rates, but also faster time of treating patients with the motion. So for instance, lung patients where we have to do the tumor scanning. Small beam emittance, again, much more conformal plans and also mini beams. And yes, reduced shielding allows reducing the footprint, as we heard, single room centers that could be placed in already existing buildings. And as we saw in the movie, here is a picture of our treatment room in Daresbury, where the patient can be both, so the images, diagnostic images can be taken in the same position as the patient is treated, which is very helpful that in reducing any positioning errors between the supine and sitting position. As we know, light can generate very small spot sizes. And actually, in order to match the standardly used 3 millimeter sigma at isocenter, and the beam is defocused. And as we can see here in this image, that's a plot of spot size of light along all the energies compared to a standard cyclotron. And in green, we can see that the light spot size is much smaller. And here it's a standard cyclotron spot size. And actually the quality of that beam, it's determined by the deterioration of the beam by passing through the degrader. And we are also working towards mini beams, aiming for 3 times smaller beam size. And here on the right, we have in green spot size in X direction. Of course, to have mini beams, we also need to adapt a nozzle for delivery. And I just refer you here to these studies that were done on that, that would allow us to deliver also mini beams. So now 2 more examples. I will show you a couple of investigations we've done with light and light mini beams and compare them with the standardly used modalities such as cyclotrons and photon modalities. And in this case, I will talk about, I will compare light to gamma knife, VMAT and IMRT, standard cyclotron. And then again, we will talk, we will compare it to light mini beams and standard spot size light. So first study case, I'll show you it's a partial left breast irradiation. And it's important to look at these cases as 25% of all cancers in women actually are breast cancers. 60% of those will require radiotherapy. But what was found that these treatments with photons actually increase the risk of cardiac toxicities, especially for the left breast cancer patients. And the incidence of coronary artery disease is of order of 10% for those patients who received radiotherapy. And here on the top, we can see a dose distribution of a patient treated with photon IMRT. And we can see this extra dose to the heart and the lung. But if proton pencil beam scanning is used, we can reduce that dose just to the tumor and surrounding tissue. And we do not deliver this extra dose to the heart and lungs. And this is just a comparison slide, just showing you a comparison between a cyclotron beam and a light mini beam that for this partial left breast irradiation. And at the bottom, we have a dose difference, a cyclotron minus the light mini beam. And we can see all this red color, it's this extra dose that would be delivered with the cyclotron, and the pink color gets up to 25% of the prescription dose. So it's a quite large amount of dose that could be actually spared if we used light. And if we look at some statistics, so looking at hotspots in the heart on these plans that I showed you, we're looking at the volumes of order of 0.03 centimeter cubed. So literally hotspots, and the cyclotron in these cases would deliver of order of 8.8 gray hotspots to the heart. For light, this goes down to 2.6 gray. And if we use mini beams, this gets down to 50 centigrade, which is significantly reduced dose. If we look at the dose to the lung, so 1% of the lung would receive close to 4 gray in case of a cyclotron, and then this is reduced to 60 centigrade and 20 centigrade in case of light nominal and light mini beam. So again, we observe this significant reduction of extra dose to organs at risk, but at the same time maintaining the same target coverage. The next case I would like to show you is the multiple brain metastasis. So these are usually palliative patients with several lesions in the brain, normally treated with the stereotactic radiosurgery, with a gamma knife or VMAT. These are hyperfractionated treatments with 18 to 24 gray delivered in a single fraction. So as we can see, in the case of a photon treatment, there is this dose buff around the brain. So we see it in the more dark color. So this is the 5% of the prescription dose. So in this case, it's 24 gray, the prescription dose. So this dose will cover all critical structures such as brainstem, chiasm, optic nerves, and damaging these can limit or reduce the quality of life of these patients. However, if we use mini beam or standard PBS light, we can create these very conformal plans of these tiny lesions, removing the dose from all this healthy tissue that doesn't need to be irradiated. And here is a study that was done together with the Cleveland Clinic, where 20 patients were studied retrospectively and compared to cyclotron, light nominal beam and light mini beam. Robustness was also included with a 2 mm setup uncertainty and 2% range uncertainty. And as we can see, going from the top left with the cyclotron, we can see this extra dose that's delivered around the tumor. And this is because of the use of the range shifter. When with light, this is reduced. And of course, with mini beams, we can see this very conformal target. And if we use apertures, of course, we can improve all the plans, and also cyclotron plan now it's much more conformal, but still light and light mini beams are even further conformal. If we can see a summary of the results on this plot where I show the mean brain dose for all the modalities. So here we have a VMAT of order of 2 gray, cyclotron, light and light mini beam, and we can see that protons versus photons, of course, there is this huge difference. And if we use apertures, this can be further reduced. So in this case, between VMAT and gamma knife, it goes down to 1 gray, mean dose, and cyclotron and light mini beam, again, it's reduced. And as we can see, light nominal beam and then mini beam even further reduces this mean dose compared to cyclotron. So improvement of over 80% was seen between the VMAT and mini beams. And for gamma knife, 2 mini beams, it was of order of 72%, because gamma knife, it's still a very precise photon treatment. Proton plants without and with an aperture had an improvement of order of 30%. Another case I would like to show you is the lung tumors. So this example, again, was 20 lung patients retrospectively studied with the setup uncertainty here of 5 mm and 3.5% range uncertainty. In this case, no motion was included. And going from left to right with the cyclotron, the mean lung dose of 3.3 gray and goes down to 2.8 if we use light nominal beam. And with mini beams, this is reduced to 2.4 gray. And if we look at this plot, looking at the target conformity, so here we have a conformity index for all the modalities. So it shows us how well the target is covered and how sharp the gradient is. So the closer to 1, the better, the more conformal the plan is. And we can see for VMAT, it's not as conformal as for cyclotron, light and mini beam. But again, the mini beams here are the most conformal. If we add motion to it, then to make the plans more robust, we have to use volumetric repainting, where we would repaint the target several times, taking into the account the breathing cycles of the patient. And here on the top, it's a plot of a target coverage. So on the top left, we have no repainting. So we can see that here, mini beams are not as conformal as light or cyclotron, and this is because of the tiny beamlets and no repainting. However, if we include repainting, all of the modalities are then very conformal, with light nominal beam being the most conformal. If we look at the dose, extra dose to the lung, and here it shows the percent of the lung that received 20 gray with no repainting. mini beams deliver the least dose to the lung than light, and then cyclotron still delivers more dose, extra dose to the lung compared to light or light mini beams. And if we use volumetric repainting, this is only slightly reduced, but the trend with mini beams being the most conformal stays. Talking about the timing, so if we do repainting, of course, the treatment will take more time. So here is just an example of timing calculations for cyclotron light and light mini beam. So if we repaint 3 times, so we can see that light is 3.5 times actually faster than a cyclotron because of these 5 millisecond energy changes. Light mini beam in this case is comparable to cyclotron, and this is because we use much more spots, so of order of thousands of spots of mini beams are needed to cover the target. So if we repaint more, of course, this number increases, but there is spot reduction techniques that actually can reduce it to comparable values. So the number of spots in mini beams is not necessarily a problem for timing because this can be further reduced. And moving to the next, so novel clinical applications. So we also looked at applications of light for flash. And when I say flash, I mean ultra high dose delivered under the second. And actually here we say under at least 500 milliseconds. And here just to show you, so flash effect, I mean, there's a huge interest in this as it promises superior tissue sparing when using very high doses, and at the same time keeping the tumor control at the same level. So here, that's actually an experiment that was done at CHUV, where a mini pig was irradiated with a very large doses of 34, 31, and 28 gray. So with the conventional timing, after a while, this necrosis of the skin appeared. But if flash was used, so the skin actually healed very well. So this is very promising, and there is hopes that flash could be applied also clinically. So we are also looking into that. So flash requires very high dose rates of order of 40 to 200 gray per second. And for cyclotron, to achieve such intensities and dose rates, a cyclotron has to run at its maximum energy, because when you go down with energy, you have to use the degraders, and that drastically reduces the intensity. So to deliver flash with the cyclotron, techniques such as so-called transmission beams have to be used, where you would place the Bragg peak outside of the target, what we see here on the far left, and the target would be treated in the beam plateau. For light, because we change the energy electronically, we don't use any degraders, the intensity is invariant on energy. So we keep the same intensity, meaning we could treat with flash or plan for flash, placing the Bragg peaks inside the target like you would normally do with a pencil beam scanning. And how does this apply to clinical plans, let's say? So we are back to our metastasis example. If we used transition beams, you would have to place the Bragg peaks outside, and the plan would look more or less like this to conform the target. You would have to go through the brain. But if you would use proton linear accelerator like light, you would place the Bragg peaks inside. So these are two flash plans. This is a light flash plan for these targets, and of course the dose difference here showing, so we do not deliver then all this extra dose to the target. So this would be a very good indication for using flash with light, so brain metastasis, that you could really spare these tissues, and especially that usually these cases are hyperfractionated, so you already have a high dose that you deliver. So if I can plan flash as good as you would treat the patient with the SRS, then that would be a great indication. And here, just to show you an example of that, of the flash plan quality. On the top left, it's the plan of a SRS plan that was delivered to the patient with the photons. And we see this extra dose to the brain that I showed you in previous slides. Then if we use light mini beams or light nominal beams, we can plan for flash with these much more conformal beamlets. So it's a single field, and we assume, yes, flash per field. And again, all this dose that we see here in red, pink, and yellow is this extra dose that will not be delivered if you would use a proton linac. And looking at some DVH statistics, so the sharper the peaks are on the right, the more conformal the target is. So here we can see that for mini beams that are dashed here, we have a very conformal target coverage. And on the left, we have the dose to the organs at risk. So continuous line is the photon plan. We can see that with the proton linac, we really deliver very little dose. And actually, in case of a chiasm or brainstem, as we can see here, we completely skip this. We don't deliver any dose to those organs at risk. And yes, when we talk about flash, we talk about dose rate. So of course, it's still not clear what is the right definition, but we can talk about instantaneous dose rate or average dose rate. And actually, these differ between the mini beams and standard spot size. So here is this example of this dose rate distribution for mini beams on the left-hand side, where we have the instantaneous dose. And this is actually of order of, so we can see it's more than thousands of centigrades per second, because in light, of course, because of the way the beam structure is, the instantaneous dose in light, it's very high. And in case of a standard spot size, this instantaneous dose, because the spots are a bit larger, it's a bit smaller, but we still get the flash dose rates. Average dose rate is higher for standard spot size because we simply use less spots. With mini beams, you need to use more spots, so this average dose rate will be a bit lower for mini beams, but still within the threshold. And for the last slide, I just wanted to have one slide of helium-ion treatments. So yes, so I guess helium promises us even more conformal plans, sharper gradients than protons, higher LET, meaning more, meaning better tumor control and treating maybe radio-resistant tumors. And here is just an example of a pediatric patient, plans for helium, proton, and photon. And we can see with photons, we would have this extra dose in the front part of the skull. With protons, it's much sharper. However, there is still this entrance dose that's delivered. And if helium could be used, this would be significantly reduced. And we have this much sharper gradients of the dose. So let's hope that we could also see helium in the clinics. So that would be it from my side. I guess two main messages. So proton linac light do show significantly higher healthy tissue sparing compared to other commonly used modalities, whilst maintaining similar target coverage. And again, linear accelerator technology is actually ideal for novel treatment techniques such as mini beams, flash, or helium ion treatments. So that would be me. Thank you.
So thank you, Anna, Alberto, and Steve. Before coming to the questions, could we take our monthly Zoom photo, please? So if you could just turn on your cameras for a few seconds, that would be great. Angelica, ready for the photo?
Yes, just
Great.
a second. Okay, one is done. Just another second, please. And, okay, thank you.
Thank you very much. So you can leave your cameras on or off if you like, but please, our speakers, leave your cameras on. So time for questions, either by raising your hand or on the chat, whichever way you would like. So please feel free. Marco, please.
So maybe I will start. I will break the ice and say there are many questions, of course, but I make two short questions if the chairman allows me, very short, and maybe
even a chairwoman actually.
Chairwoman, sorry.
Say that.
Kidding, go on. Go.
To Alberto or to Steve, whoever wants to answer. So the first question is, what is exactly the roadmap to the first clinical treatment? Where is the first clinical treatment occurring? When and in which kind of disease you think it will be? And the second question is the positioning of the patient. I see from the pictures, but it was not described in great detail, that you have a chair and apparently you have also a vertical CT for planning. This looks to me similar to the commercial systems now, like PQ or Leo Cancer Care. So I wonder if you are having your own internal development or you impose on what is now on the market. Thank you.
So, Alberto, do you want to answer?
Well, I can give a short answer and maybe you can complement, because then yeah, the roadmap to first patient treatment, as I mentioned, we need to go through the full verification and validation test of the full system. At the moment, we have the beam production system mainly installed, but we still need to do the full end-to-end test. So this will imply a lot of testing time, and basically from that moment, and also validation from the radiobiological perspective of cell irradiation, and then first patient. And that's what was mentioned, is will be done in Daresbury, at the Daresbury site, in collaboration with University Hospital of Birmingham, as clinical user and clinical radiation oncology department. And on the second question, it's more about the let's say delivery system and patient positioning system. Yeah, we use CT scanner and chair and the positioning system from PQ, which actually was a collaboration already set up many years ago when we started the project. And I think Leo Cancer Care now has very rapidly developed and now also basically, delivering similar system. But the idea, is a seated position with a robotic chair and in-room patient imaging. Yeah.
But if I can just finish, so you don't have a date, you don't have a timeline, and you can tell me when the first patient is supposed to be treated.
Maybe Steve, if you want to answer.
Well, it depends on many factors at the moment, so I don't think I can give you a definite date.
Okay, thank you.
We're dependent on other people, of course, and on the regulatory people and on the clinical people.
Thank you. So there's a question for Anna from Marius. As you know, FLASH requires high dose, not only, also to the healthy tissues. So conformity of the treatment becomes less important. Can you comment on that?
Yes, of course. I didn't actually say it, but that's true. And the plans I showed you, I'll just quickly share the screen again. I assume every time I plan FLASH per field, and all the entrance dose is FLASH. So just to show you here, so I use thresholds. Of course, it's still not clear what is the minimum dose that's needed for FLASH to appear. So as you can see here, for instance, that shows the amount of dose that was delivered in this case with the FLASH thresholds. And in this case, it was 40 gray per second. So 4 gray minimum dose, 40 gray per second dose rate. And we can see all that area would meet this.
We don't see your screen, Anna.
No, okay, I thought I'm sharing. Okay, 1 second. Again, now? No.
Yes, yes, thank
Okay.
you. That's fine, that's
So
fine.
what I was saying is, so this middle picture, so here we have a dose distribution of a flash plan for this lesion. And this shows, so I'm using thresholds when I plan, so trying to have the minimum entrance dose to allow for this flash along the way to the target, because we hope for this effect. So this shows how much percent of this dose met the flash thresholds, meaning the minimum dose and dose rate. So in this case was 4 gray minimum dose at least and 40 gray per second. So you can see that 100% got it. So yes, this is definitely the point of flash. So we want the flash at the entrance to spare, to have this flash effect. But of course, if we want to transfer it to clinics, if you were to irradiate half of the brain, saying it's flash, I'm not sure if this would be so easily accepted in the clinic. So providing plans that can be as good as what's currently delivered, I think it's the way in for trying out flash in clinics.
Okay,
So,
thank you. Jeff, you had your hand up?
Yes. Excellent talk. It's really exciting to hear about all the progress, and I want to just congratulate the speakers at every level for the work they've done. I've been following this closely for years. The question I have 2 questions. One, can you switch rapidly between spot sizes on the machine dynamically? And 2, have you looked at LET? Because LET is high at the edge of beams, and if you have a very small spot size, you're going to ramp up your LET, and that may have interesting biological consequences. Have you looked at LET with the mini beam? Over.
I can answer the LET stuff. We are looking at this, but I don't have anything to show yet. But we are also taking into the account LET in our studies.
Okay. Thank you, Eric. Please.
Hi, yes, can you hear me?
Yes, we can. Thank you.
Hi, yes. Yes, I'm Eric van der Kree from IBA in Belgium. So thank you for the talk. I had a question on the accelerator side. You mentioned that you think about helium or other ions. Do you already have experience with it experimentally? What's the status on this?
No, the answer is no, we don't have any experience with it. We've been concentrating on protons for the moment.
Okay, thanks.
We've done sort of a feasibility study, mostly by Alberto, but to show that it will be possible. But of course, we have a very clear objective at the moment, and that's to treat the first patient with protons.
Of course, yeah. Okay, thanks.
Thank you. So good. Your turn now, please.
Yes, first of all, again, also from my side, thank you to these very nice presentations. Well, I contacted Alberto in 2016, and because I was working with a group of Professor Dolling and Professor Reindl doing mini beams for spatial fractionation in that case. And we were from that time convinced that your machine would be the best option to have really mini beams below 1 millimeter in AVO-A.D.A.M or sigma to do spatial fractionation. So and it's great to see what you achieved now in these past years, and we are looking forward to hearing about first patients, although we do not know the date. But my question is very short to Anna, since, as I said, we're here in Munich very much interested in the mini beam option. So your treatment plans, when you were showing the light mini beam option, what beam size in sigma did you assume for your mini beam treatment planning? I think you said it, but I'm not sure anymore.
Yes. So 1 millimeter sigma at isocenter 230 MeV. So it's still quite large, but it already makes significant improvements, right? So this is, I guess, the most reasonable or conservative approach to mini beams.
Yes. And maybe just a second question for the future: do you also consider to go to a smaller mini beam so that a spatial fractionation with like dots in a certain distance that is much smaller than the beam's beam size can be achieved with your system?
So from the clinical point of view, we will definitely look into this, but from the technology point of view, maybe Alberto or Steve can comment.
Yeah, maybe let's say with the present design, we look at the conventional dose delivery with pencil beam scanning, and so not a mini beam dedicated. In terms of beam emittance, we should be able to achieve such mini beams, but then of course we need to adapt as well the beam transport and dose delivery for achieving that, meaning either preclinical or clinical settings, but of course with a dedicated dose delivery, I think.
Thank you.
So I have a question, if I may take the privilege of chairing this thing. So Steve and Alberto, as you know, lots of people with lots of creative ideas want to be able to go from a research idea to a concept to a facility application. So what is one piece of advice that you could give them, having gone through the process? Steve?
One piece of advice.
Well, more than one piece, but at least one.
It's a tough. I mean, I thought the technology was the tough thing. Now I realize that going from research instrument to something which you can sell is much, much more difficult than doing the initial part. And probably the most difficult of all is getting the funding to do it. So those two things we sort of ignore when we do the technological development. But two very important points are all of the regulatory, the V&V, which is maybe gone through by Alberto, who's now become an expert. But also, I mean, I spend most of my time now looking for funding, to be honest.
Yeah.
So those two things are the things, and I mean, you've seen from the work which Alberto has shown, the complexities there are in going through this loop, going from, and I think it was a very useful question which you asked for this presentation. How do you go from a research instrument to an industrial or clinical instrument?
Yeah. Thanks, Steve. So the other thing for Anna and Alberto, so what is your next biggest challenge from the medical physics point of view, Anna, and Alberto, from you going to the device? Anna?
The biggest challenge, so I guess we have all these studies and clinical indications prepared, and now I guess verifying this in the treatment room, preparing QA plans for that, and checking that will be, I guess, not the challenge, but also a necessary step to see how close or how far from the reality are we. So yeah, we can plan as much as we want, but the reality will be in the treatment room once we have the beam.
Alberto?
Yeah, well, one of the biggest challenge I think now is the reproducibility, because one thing is getting the beam out of the machine. The other thing is making it stable and reproducible every day. So really going from the first beam to everyday beam. I think that's one of the biggest challenge. And if I can add on what Steve also mentioned before, I think the important key ingredient is also, well, patience and endurance, and yeah, just continue.
Funding.
Yes.
Funding. Any other questions from anybody else in the audience? Yes, Vikram, please.
So I want to compliment the team, but I want to follow up on the answer that the team just gave to your question. So there are two aspects. In terms of showing a benefit to patients, as you know, we've been running randomized trials of protons versus photons now for almost 15 years, and we still don't have clear answers. So that's a very high bar. Now people are still buying building proton facilities. So what is your estimate? Maybe I missed it, but in terms of reducing the cost, what kind of magnitude are we looking at if you were to bring this to production? How would the cost compare with an existing proton facility?
Okay, now I have to look into a crystal ball. I know what the standard answer is, but if you want my opinion, I think if we get within a factor of 2 of photons, the highest level most complicated, most expensive photons. If we can get within a factor of 2 of that, it will be a big, big success. The hope is that we'll do better, but it's a long haul to bring down the price, as you know, and the size and all the problems with construction and so on. I mean, electrons are much easier, but as you all know, they're not as good. And so I would guess, and I wouldn't like to be held to this, but I would guess that in fact, if we could reduce the total cost to a factor of 2 above what the most expensive photon system cost, then we would be in a very good position. I don't know if you agree with that, Vikram.
And what kind of investment would you need to get to that proof of concept?
Another very difficult question. Yeah, maybe the IBA guy could answer it better, that he's more experienced than we are.
I was actually going to ask Eric if he could make a comment on that, actually.
I could make a comment, but it wouldn't be an intelligent comment.
Eric? He's not there, I don't think. He might have gone. So if not, so then actually I see that Francesco's hand is up as well. Sorry, Steve, we are asking difficult questions, but that's our job, right? Francesco.
Yes, thanks. So thank you for your nice presentation and these promising developments. I see this machine allows for a certain high degree of freedoms in terms of changing different parameters, which is nice. And on the other side, of course, you have to be able to control also in a very reliable way all these different parameters to have a full control of this configuration. So I was wondering, maybe you mentioned in the presentation, but I was wondering if you are you looking for a more advanced and specific beam monitoring system, or are you thinking to use something which is already existing with maybe some modification?
Alberto, I can answer, but you'd be better placed to answer.
Well,
I'll give a quick one. We have a very good beam diagnostics and beam monitoring system at the moment, and it's a very highly developed system. But your question is, would we like to go further? So maybe Alberto would answer that.
Yeah, I think, well, it's a bit of the two that you mentioned. We have some dedicated beam monitoring system. For instance, for the energy of the beam, we really have developed quite sophisticated algorithm and device to monitor the beam energy. And then, of course, there is the dose delivery system that also need to take into account a pulse beam with high peak current. And this is also something that is being developed. So some is standard, some is advanced, and maybe not commercially available, but modified off the shelf or even in-house developed devices.
So thank you. So it just remains for me to actually thank our 3 speakers for a wonderful session and being able to also address some provoking questions, shall we say. So thanks a lot. A really, really enjoyable session, and it's wonderful to see that light has come such a long way, and we might see the light at the end of the tunnel very soon, right? Steve, Alberto, and Anna. So thanks a lot. Have a nice evening.
Thank you very much.
Thank you.
Thank you.
Bye-bye.